Thank you, Mr. Chairman. Especially for the people who are new in this domain of organic-based photovoltaics, I would like this afternoon to highlight some general aspects related to processing and lifetime. Why? Because these subjects are becoming of crucial importance for this field. So I would like to start with a short historical situation on the era of organic-based photovoltaics, then move on to a very general description of processing and what are the challenges of processing. And then in the last part, I will give a more detailed description on issues related to lifetime. In 1954, on the front page of the New York Times, there was a very small article, but a very enthusiastic article, and it spoke about an invention done at Bell Labs, and it was an invention based on silicon, and that was able to transform light into electricity. And it had an efficiency of 6%. Since then, 1954, we've seen that this invention based on silicon from 6% moved on, and now if we look to our roofs, we encounter very often these black things or blue things that generate electricity, our silicon solar panels that can reach efficiencies around 20%. So from 1954, from 6% silicon moved to solar cells nowadays, commercially available, around 20%. So that was one important thing that happened the last years, that this silicon became always better. But next to that, we had some other players coming around. We really came to a kind of biodiversity on PV, a kind of zoo, a photovoltaic zoo. On this photovoltaic zoo, you can see here again in blue the silicon-based solar cells. On top, even reaching efficiencies of around 40%, we have tandem solar cells based on inorganic semiconductors. These are quite expensive and are mainly used for aerospace applications. But what is also very interesting, certainly for the winter school of these days, are these emerging photovoltaic technologies. These started not so long ago, if you compare it with 1954, and they made a very rapid increase. Which are these emerging photovoltaic technologies? Well, we have the dye-sensitized solar cells, the organic solar cells, the quantum dots, the hybrid solar cells, and the last player that came around were the perovskite solar cells. So these are all solar cells that have, on some aspects, a relation with organics. So we can say very generally these are organic-based solar cells. So we've seen an enormous increase the last years, but if we go back to the pioneering years, really the pioneering years, what made that we came to these high efficiencies that we have now? Well, it was a very strong interplay between materials, physics, because if you look to the history of, for example, organic solar cells, all the progresses that have been made, increases in efficiencies, were always related to new materials. So that forms really the basis towards progress. We had polymers, small molecules, fullerenes. There was progress on metal oxides, and the last years a lot on perovskites. And the very nice thing on what our colleagues from chemistry do is that with these materials, they really can tune electro-optical properties, they can tune morphology, they can tune viscosity. So this is really of crucial importance to the progress in this field. But materials on itself is not enough. You have to understand what you're doing. So there has to be some feedback. Are these new developments successful, yes or no? Some from the physics, characterization, device physics, modeling, preparation of lab prototypes, they really led to a better understanding of what is going on. And it is this interplay that really made that these emerging photovoltaic technologies made this progress to these high efficiencies. Now we are entering a new phase in this evolution of organic-based photovoltaics. Since we have already these very promising high efficiencies, we have to go a step further, and there processing and lifetime becomes really of crucial importance. The first thing is the upscaling. So as we had before this 100 years ago, these first planes, that was really magic, that a person could fly in a machine throughout the year. What you've seen is there's been an upscaling, that we have very large aircrafts, and in 100 years they managed to improve from 1 person to 800 persons in an aircraft. So that was an amazing progress. But if we look to the challenges that we face in the organic-based photovoltaics, it's even more. So we are very happy in the labs if we can make these tiny solar cells with nice efficiencies. We are even more happy if we can make them flexible, transparent. But if we really want to go to the real field, really to put solar cells in real life, we don't need these small things, but we need millions of square meters of solar cells. So the translation, the upscaling that we have to do is enormous. So it's really a big challenge that we are facing the coming years. How can we do this upscaling? Well, it's very important to know that there are 2 main routes in this processing. You can have a route on vacuum deposition, and you can have a route of wet deposition. I'll give you very briefly some cartoons or working principles on this. So this is on vacuum deposition. This is a cartoon provided by Dresden University. What you would like to do there is you would like to make these very thin films, because in a solar cell you need a sandwich structure, or you need many films one on top of each other. So what's the principle there? You have your vacuum chamber, you have your crucibles with this, various materials that you need, and you apply your substrate. It can be glass, and then step by step you have your substrate is glass. You have your first transparent conducting electrode that you can evaporate through 1 crucible. You go then to your organic photovoltaic layer. There you need the other crucibles, and so on, moving to the top metal. So you really are able, with this vacuum deposition technique, to apply the various layers that you need towards a working device. The nice thing about these vacuum deposition is that you really can control the thickness very nicely. The vacuum deposited layers have very nice properties, so it's a very controlled way to work with. One of the main comments is, this is very nice, you can have very nice efficiencies, 12% obtained with these kinds of organic solar cells, but can you go to upscaling? Well, also there, it's important to know that also there are a lot of activities worldwide. People are trying to come to vacuum deposited roll-to-roll systems. So it's the message that I would like to bring is roll-to-roll is not something that is only for the wet solution. Also with vacuum deposition, this route is possible. I know that around Dresden, with Heliatech, Novalet, there's lots of activities around it, but also in the Aachen region, there's lots of pioneering work on this field. Let's move now to the other route, the wet deposition. The wet deposition uses inks based on polymers, can be also processable small molecules. And there, the nice thing is that we really can use printing techniques that have evolved the last centuries. You can use screen printing techniques. Spray coating is like if you have making these tags on the walls. You can use inkjet printing. So your functional inks, your polymers, become ink. Which technique should we use? Well, it depends what kind of application that you want and which resolution that you want. So this gives a scheme. What you find on the y-axis is the printing throughput, so how fast is your printing technique, and what you see here on the x-axis is the printing resolution. So if you want to print very fine lines, you have to go to the left side. If you have to go to large area, large output, so fast printing, you have to go in this region. And this is also the region needed for solar cells, because there you need really a huge amount of square meters. Is this now really possible to use these kind of wet deposition techniques for organic-based semiconductors? Well, it is. Already many years ago, here in Flanders, we had pioneering work from Agfa, that is Mortsel, Antwerp. They come from the classical film photography industry. And if you visit the factory, they have really rolls of various meters, enormous rolls, all based on this PDOT, so this conducting transparent electrode. And this is really printing or coating 200 million of square meters per year. So it is possible to deposit, to come to large area depositions of these functional films. Closer to here, we had some years ago, we started with a spin-off company, Lumosa, and the very nice thing also of Lumosa is that it has shown that it's possible to use screen printing, also a very traditional printing technique, to make large area, to print large area flexible hybrid displays. And here also in this meters high light-giving film, organic semiconductors have been used. So it's possible even for a small company to print large area organic-based semiconductors. What about solar cells? Well, also there, it's nice to show this pioneering work from Denmark, from the group of Frederik Krebs, where they demonstrated really the first solar park based on organic solar cells. And the installation of this solar line, it was just on a roll of solar cells. It was rolled off, and they claim to have the most fast installation of solar cells compared to all other techniques. Not so far from here, I would like perhaps also to highlight this roll-to-roll OPV line installed by Solvents. This is also a recent development, and I think also the coming years we'll hear much more about this. When you come to this upscaling, it's important that it's a robust process, that when you print today or you print tomorrow, you always have the same quality. But what is also very important, since we want to make kind of green product, renewable energy, solar cells, you need to use environmentally friendly solvents. You don't like to use chlorobenzene of these kind of solvents. So it's very important to also work on these green aspects of this production, of this processing. Also, that is a very important challenge, and also there, the interplay with the chemists is of crucial importance. Just to give you a flavor of one of the creative roads towards this green production process, I would like to highlight the work of Lien Dolieslager that has been presented also yesterday in this winter school. It's that there the idea is to go to a processing where as a solvent you don't use chlorobenzene, but you use water. So the route there is to make nanoparticles based on state-of-the-art semiconductors. You can make blended nanoparticles where you insert also PC70. And the nice thing about these nanoparticles is that they can be applied, for example, with spray coating and using water as a solvent. So that's one of the roads that we are working on, and also on this manuscript is in preparation. To give you a more general idea about these green aspects, besides the solvents, green means also how much energy do you need to prepare these solar cells. And that's what has been called the energy payback time. It means how much time should a solar cell of a given technology work to generate enough energy to compensate the energy that you need to make it. Well, if you look to this list of renewable energy technologies, you can see that for the OPV, we have a very low energy payback time, 0.3 to 0.5 years. So after a few months of operation of organic solar cells, you have generated enough energy to compensate the energy that you needed to process it. If you compare it, for example, with silicon, here, you see that silicon is higher, but you can compare it also with other ones. So the OPV is really a champion in this energy payback time. One of the aspects that's very important in this energy payback time is the amount of heat that you need. So if you want to use a technology where you need very high temperatures for your processing, there you'll see that the energy payback time will increase. So also there in this process, it's very important that we have new ideas and new concepts coming from chemistry. That was very shortly what I would like intended to tell you about this processing aspects. And now I will move over to the second part of this tutorial. It's related to lifetime. Since lifetime is related to stability, reliability, what I would like to start with is giving you some general concepts on how to study lifetime. What is a generic lifetime study strategy? After an introduction of some of these definitions and activities, I would like really to use this lifetime study strategy as specific on OPV, and I will end with looking in detail to one aspect of lifetime, is the relation of thermal stability and the morphology. So if we look ahead of this organic-based photovoltaics, what are the three main challenges? The increase of efficiency. We've seen that this went very fast the last years. Robust and green production processes. And the last one is the increase of the OPV lifetime. If we look to the silicon solar cells, the warranty that you get is 25 years. Some years ago, you could buy one of the first commercial applications based on organic solar cells. If you read the very small lines on warranty on this product, you can find a warranty of 1 year. So you can see there's quite a discrepancy. There's a long way to go. But people have experience in extending the lifetime of organic systems. For example, a very famous organic system are humans. If you look to the lifetime of humans around 1840, 1860, the lifetime expectancy was less than 40 years. So you see also there, new insights, new progress led to increase of the lifetime of this organic system, and now life expectancies can be reached around 80 years. So it's a doubling of lifetime. We don't want to have here a doubling, but we are more ambitious. Very generally, how can we increase lifetime? Well, from the past, also when we studied before the lifetime and the stability and reliability of the traditional electronic systems, we used this approach. And this approach is based on understanding of the failure mechanisms. So what we say is that when we look at the system and we look how the system degrades, it's a black box. And you have really to know in this black box which are really the failure mechanisms that are occurring. The strategy that we use to study this lifetime consists of 3 parts. We start first with the reliability assessment. We want to know where are the failures, how do these failures look like, what is the cause, the effect, the mode, frequency. When you identified these failures, you have to know how does it work, what is the failure mechanism. And if you know how the mechanism works, you can come to a model. Why is it important to have a model? Not only from a scientific point of view, but a model is crucial if you want to do lifetime predictions. So if you want to come to a lifetime of 25 years, you're not going to do field experiments of 25 years. You want to do tests on a shorter time scale, and based on these tests, you would like to predict what will be the lifetime in normal operation conditions. So what are the tools that we need to come to this kind of lifetime study strategy? Well, for the reliability test, you can use this kind of climate chambers where you really can change stress parameters going from temperature, humidity, light, and so on. You have to measure really a population of samples, and when you have a population of samples, you can have a proper statistical analysis. To do this predictions, you need to know how do these defects or degradation look like. So it's very important to open the black box and to use specific analytical techniques to know what is going on. And if you bring all these three together, you really can come to a reliability evaluation, but also more important, the lifetime prediction. So let's start with this reliability tests. What is the goal of this reliability test? To estimate the reliability of components at normal operating conditions. And there are now two types that you can use. You can use the so-called real-life tests, or you can use accelerated tests. So the real-life tests, you can call them also the IKEA test, so you won't forget it. So you monitor the reliability of a statistical population under normal working conditions. So you're not going to increase the stress. And there you can do a stressing during the expected lifetime, or you can do a number of cycles, like here in this IKEA test. If during the life of this chair you're going to sit there 10,000 times, they're going to do this test 10,000 times. So these are the real-life tests. Tests really during normal stress conditions, but with the necessary repetition. You can go also to accelerated life tests. So there is the idea, again, it's always important that we look to a statistical significant population of samples to see how they behave at accelerated stress conditions. Why do you need a population? Because the distribution, what is the statistical distribution of your failures, is very important, especially when you would like to do the lifetime prediction. And as mentioned before, the model is crucial. Just a simple example. Here it's capacitors based on a polymer, PET capacitors. And what has been done here is these capacitors have been brought to 125 degrees Celsius, a voltage of 150 volt. And after some time, you see that some spikes occur. This is a breakdown. So what you can do here is for this population, determine what is the failure time. When you have this failure time, you can plot them in this kind of aging curves. You have the percentage of failures over the time. And depending on which voltage that you apply, you can, if you go to higher voltages, your failure times comes earlier, lower voltages later on. From these kind of plots, you can determine what is the failure distribution. You can try out your model, and based on this model, you can do a prediction to operational lifetimes. So this is, here we use voltages that are much higher than the normal operational voltages, but by the proper model, you can really see what will be the expected lifetime at normal conditions. Here it's easy because you see that all these failure times are on one line, but that is not reality. Certainly for new technologies like, for example, organic-based solar cells, you're not going to expect one line of failure times. This is perhaps something that will look more realistic. What we see here is the dielectric breakdown for traditional silicon oxide. And if we have again this failure plot, what we see here is not one single line, but also here's some deviation. These failures, they come earlier in time than this class of failures. So what we call this a bimodal failure distribution. So if you do a test and you have, for example, from your test on one sample, you have this failure time, and you do your prediction, you can imagine that you get an overshoot of your lifetime. Sometimes people, when they see this short failure times, they discard it. They say it's an outlier. But that's the reason why you need a population of samples to really see, do we have these extrinsic failures? Because if you look again to how is the failure occurring in organic systems, if you take again the model system of human beings, also there, if you look to the failure rate, we have this kind of bathtub curve. You have a very high failure curve in the beginning. These are the kind of what is called infant mortality. Then you have a kind of normal constant failure rate, and then at a given moment, this is the failure rate that comes up. That's statistics. But this kind of statistics, you don't only find it for human beings, but you find it for all types of applications, electronics. And this kind of bathtub failure curve is also expected for an electronic systems like solar cells, for example. What we've seen in the past is that you had European electronic products and you had the Japanese products. And at a given moment, people said Japanese products and German products, they have a very good, they're very reliable. But what happened there is that these products, they had a very low infant mortality. So when you bought such a product, it lasted for a long time, and certainly you had this amount of infant mortality was very low. And there are tricks to get to it. So you can have products where this infant mortality is taken out. So when you buy, you can buy products where this is shifted out, and this is what is called burn-in. I know that people use, certainly in this domain, burn-in to describe certain mechanisms, but what is really burn-in? Burn-in stands for screening, so it's a process where you bring all your samples that you would like to sell, you give them a pre-treatment so that you can take care that all this infant mortality are taken out. So another graph to illustrate this. So in normal field conditions, when you buy a population of telephones, for example, some of the telephones will fail really in the beginning, and some will fail after some years. What you could do if, is that if these telephones are failing, for example, by a given stress parameter, if you bring them to an accelerated stress condition, you can take care that on a short time they're stressed so much that you can check which are the ones that have failed, so that you can take them already out. So the population that you're going to sell are the ones where you have eliminated all the products with these early failures. That's burn-in. How is this done in reality? You can do it with temperature. So a number of these samples are brought to high temperatures, and afterwards you check them which have failed, you take them out. You can do it with thermal cycling. There are some components that fail due to temperature differences. So you can use these kind of tests, or if it's a mechanical failure, often they use mechanical accelerations at very high accelerations. So that way you eliminate these early failures. Just to give you an example, here are some, I don't know if these are mobile phones, they're all brought together and given stress chambers for burn-in tests. After this test, it can be seen which are the ones that have failed, and you take them out, and you can do this, for example, also for lamps. That is what burn-in is all about. After these very generic definitions and aspects of reliability study, let's move now to this lifetime study strategy, especially for the organic-based solar cells. If we look again to the first aspect, the reliability aspect, if we look to this black box, in literature already you can see really a huge amount of kind of failures, of type of failures. You can encounter degradation of electrodes, degradation of the photoactive film, morphology can change. So there's really a multitude of failures that can occur. So when you say my solar cell has failed, you have really to know why did it fail, which of these failure mechanisms is the most important. How can we prevent these failure mechanisms? And so to study them, to know what are these failure mechanisms, as said before, you need appropriate analytical techniques. This is a very nice review paper from Jorgensen. It's from 2008, but it gives you already an idea. If you really would like to assess the failures that occur, there's really a multitude of analytical techniques that you can use to really know what is going on, what is the mechanism that is occurring. That's to disclose your black box, to know what is really happening in your device. Of course, you can do the IKEA test, to do the real life test, and people are doing also that. This outdoor testing, this is already some example of what has been done some years ago. But what could be the result of this outdoor test? So after 14 months outdoor, people have seen that the efficiency increased, the VOC went down, the current didn't change, and the fill factor also improved. That's the result, but you don't know what happened. More recent report, also from outdoor testing. The nice thing about it is that this is a test of 1 year. 1 year testing in Holland, Denmark, and also in India. And there it's nice to see that the changes are much less than seen before. But again, also here, why do we have this degradation? That's also not really clear. And you're not going to do this outdoor testing for 25 years before you're going to sell it. So you will need some accelerated aging tests. To do that, various labs are starting or have started to do this kind of indoor test, accelerated aging test. Here at IMOMEC, a solar reliability lab is present, where these reliability tests can be performed under various conditions. These are very large chambers, so you really can measure a population of samples. You can do the statistical analysis, and also with the analytical techniques, you can have more insights in what is going on. So this is certainly something for the near future. If you really would like to predict what will be the lifetime of organic solar cells, such a kind of approach will be needed. To give you an example, how to come to a kind of lifetime prediction model, we'll focus in the coming slides on what will be the effect of temperature. We'll isolate one of this multitude of failures, just temperature. What will be the effect of temperature on solar cells? How are we going to study this? Well, we're going to bring these solar cells in an oven, and it's not that we're going to measure it only before and after this thermal treatment, but we're going to measure how the electrical properties are changing during the thermal aging. So in situ IV measurements, we do it in dark and in light to really see what is now the effect just of temperature, what is the combined effect of temperature and light. We have some advanced electro-optical techniques. Since we want to know what is going on in the material, the black box, we'll see at a given moment that the morphology will play a role, so techniques like TEM are important, and thermal analysis. So what we'll investigate in the coming slides is what is the link between the photovoltaic behavior and the morphology at higher temperatures. If we look to a model system based on P3HT PCBM, we bring the system at an elevated temperature, 110 degrees Celsius, and we keep it in dark, and at intermediate moments, we measure the IV curves. What we can see is the change of, we'll see that the short circuit current will change over time, and what we put here is a relative change of the short circuit current. So we start from 1, and then we see relatively what is the short circuit current doing. What we see very surprisingly is if you do the aging at 90 degrees Celsius, the current goes up first and then starts slowly to go down. If you go to higher temperatures, you'll see that the decrease will be more and more severe if you increase the temperature. So this is a black box. If you see these curves, you see it's a black box. Where does this degradation come from? Well, when we used TEM to look at the morphology, we saw that there was a very nice link. So this initial increase was due to improvement of the morphology. The P3HT in the system became more crystalline, so the electrical properties were better. But after some time, this decay was very nicely correlated with the formation of these dark spots in the TEM images. And what are these dark spots? Well, in the beginning, we have a very fine mixing of polymer and PCBM fullerene. But due to the temperature, we'll see that these fullerenes become more mobile and they cluster together. You have here all these large black spots are clusters of fullerene. And you can therefore imagine if the fullerene goes away from your photoactive layer, that your solar cell becomes worse. So this is really clear. Temperature has an influence on morphology and therefore also on the photovoltaic properties. Now that we know that, it would be nice, since we know it's something that has to do with diffusion, this fullerenes are moving, it's temperature driven, can we put some model on it, some even semi-empirical model, to come to some lifetime predictions? So we tried that for now the model system MDMO PPV PCBM 1 to 4. Here you see in the colors the degradation points for the relative change of current at various temperatures. Now it's between 50 degrees and 90 degrees. Higher temperature, rapid decrease. Well, what we said is it's a diffusion model, so a square root of t is important. It's temperature driven, so we have a kind of acceleration factor that we are going to insert in the equation. And since it's thermal driven, let's use an Arrhenius relation, so with an activation energy. Well, when we fit these curves with this formula, we can really see the dark lines are the fit based on this semi-empirical formula, and it gives a very nice fit. You can, from these fits, you can determine what the activation energy, the K factor is. You get a very nice line in an Arrhenius plot, and you can determine your activation energy. And if you know your activation energy, you really can do predictions to whatever temperature that you want. That's what we tried. So using this formula and the determined activation energy, we said, let's predict what will happen at 20 degrees Celsius, so at room temperature. The prediction, the calculated line is this one. What we also did, we really measured solar cells at that temperature, and you see that it was really coming on. So this is kind of approach that you can use to do very short lifetime tests at accelerated conditions, but you can get out these kind of accelerated aging models where you can do a lifetime prediction to whatever condition that you want. But sometimes it's not so easy. So these polymers sometimes behave quite strangely because an illustration is given here. We have again P3HT PCBM 1 to 1, and we went to various temperatures. And what we've seen is 125 for 15 minutes, 2 hours, 24 hours. But then when we stayed for 2 hours at a lower temperature, you saw that it had less crystallines than 2 hours at 125 degrees Celsius, as you expect. But when you go to a higher temperature, 2 hours at 150, you even have less crystals. Normally, if something is thermally activated with an Arrhenius relation, you would expect that how higher the temperature, how more rapid the degradation, and in this case, how more crystallines, PCBM crystallines that you would have. So this is really an anomaly. Can we understand how what's occurring over here? Well, therefore, we have a very nice collaboration with the colleagues of the VUB in Brussels, where they can have very sensitive thermal analysis measurements. And what they've seen is that when we look at this system, that if we measure the crystallization rate, this crystallization rate, it's low, then a given moment becomes maximum and then becomes low again. And this is really related to a melting point and a glass transition temperature. And in between it, just in the middle, you'll have, based on thermodynamics, you will have an increase of crystallization rate. And that gives an interpretation why we see these anomaly effects. And that's very important to have these know-how, because if you want to have good lifetime prediction models, you have to take this into account. Up to now, I've shown you temperature affects morphology and affects the photovoltaic parameters, especially the current. Well, I'll show you now that it's not only the current that will be affected. What we've seen is that if you look at the VOC, after aging, the VOC goes down. But we measured with Fourier transform photocurrent spectroscopy at an elevated temperature how this ECT, the energy of the charge transfer complex, is changing. And very surprisingly, we saw also the same kind of evolution. So what happens when you have a thermal treatment, the PCBM comes together. You will have this kind of clustering. But when you have this kind of clustering, if you look to the energy levels, you will have kind of broadening of these energy levels. And when you have this broadening of energy levels, you'll see that this effective band gap is smaller after phase separation than before. And if this effective energy band becomes lower, also your VOC is becoming lower. So what we've seen here is that temperature, when it affects morphology, does not only affect the current, but also the voltage. So in summary, we can say that the morphology of model bulk heterojunction solar cells is thermodynamically not stable, and that annealing leads really to a kind of phase separation that will influence the current and the voltage. This is when we go to high temperature, but remember, this is done in dark. So now we said, let's do systematically, let's put also some light on it. So now it will really degrade as hell. And that's what we've done. So we went to a temperature of 85 degrees Celsius. This is how the P3HT PCBM looks like after 62 hours at 85 degrees Celsius. But when we look at similar films, when you go to these temperatures and you put also light on it, the surprising thing is you didn't have any phase separation anymore. So if you go to high temperature and you put light on it, the morphology behaves better. So what is going on over here? So what we've seen is that by applying light, you have light-induced dimerization of PCBM. So the PCBM that before is separate can form dimers, and you can imagine when dimers are formed that the diffusion becomes less. So that was a really important new insight towards the stability of these bulk heterojunction solar cells. It has even been shown by colleagues from Imperial College that if you give a light pre-treatment at room temperature, so you make your film, you give it a light shot, and you go then to higher temperatures, that your film also behaves more stable. The only thing that it's very important also to mention on this is not a solution. Don't think now that if you go to high temperature and light that it's solved. We have seen if you go further to elevated temperatures that this is reversible, that these dimers can dissociate again. So the problem is not solved. And also it's not really clear at the moment what the effect of this dimerization is on the PV characteristics. So I've shown that temperature can have an important effect on the morphology and stability. So if you know that this problem occurs, you know in which direction to look for a solution. So from the collaboration with the chemistry, we've seen that increasing the glass transition temperature of the donor polymer is really a very attractive road and a very effective road. So TG, how higher your TG, how better the thermal stability of your morphology. That's also been seen here at the chemistry part of IMO Mech, that the introduction of functionalized side chains to the donor polymer really gives an increase of stability. Yesterday, there was a manuscript submitted by Jürgen Kestes that has been accepted for chemistry of materials. So to have a nice paper on this effect of these functionalized side chains, please have a look to this new publication. So we mentioned the effect of light-induced PCBM, but there are also other routes that can be followed. To have a general overview of these effects, I can also refer to this review paper of Ilaria Cardinaletti that has been published in June of 2014. Is now this temperature effect only a problem of the pure organic solar cells? Well, you all now know that at the moment the perovskites are really a new player in this field. Let's have also a look to what happens on the effect of temperature on the perovskites. So for the perovskites that we are going to look at, methylammonium lead iodide chloride, what you're looking here is to a stack that is not the complete solar cell, so we left out the top electrode. And what we did is first we looked at room temperature. If you look to the morphology, you see this very granular structure, depending also on the density of your solution. In the beginning, you will have a completely different initial morphology. But what we wanted to do is to bring this stack to a higher temperature. And there are these kind of standard tests that you can perform for solar cells. So we went for some time at 85 degrees Celsius. And a very nice result is shown here. If you bring them for 6 hours at 85 degrees Celsius, you see here a platelet. After 12 hours, you see more of it, and after 24 hours, even more. So it looks more like these kind of biscuits. So temperature is not only affecting the pure organic solar cells, but has also an effect on the perovskites. So this certainly deserves to be studied more in detail. So if we come really to a general conclusion for this field, what are the main challenges for the organic-based photovoltaics, very generally, from the pure organic to also the perovskites? Increase of efficiency, that remains. But very important, I hope that I have convinced you that a robust and green production process is really of crucial importance if we really want to bring this technology to real life. But also the increase of lifetime will be crucial. It's good to have better insights in the multiple failure mechanisms that can occur so that you really can provide appropriate solutions. Also very important, and up to now I've seen very little reports on that, to study a population of samples, not just one sample, but because this can give you really some wrong ideas. If you now look more specific to the thermal aging aspect, we've shown that for the organic polymer fullerene solar cells, you've seen that these are not stable at a higher temperature. The morphology will change, your voltage will change, your current will change. There are very promising routes to improve the stability, a route of high TG materials, use of side chains. And also for the perovskite, the new materials with the high efficiency, also there is of crucial importance to study the degradation mechanisms, and in particular also the relation with temperature. So that brings me back to the initial slide that I've shown from 1954. I told you that it was quite enthusiastic. At a given moment, they write, it may mark the beginning of a new era, and it can lead to the realization of one of mankind's most cherished dreams, harnessing of the most limitless energy of the sun for the uses of civilization. So you see, very enthusiastic. So I would like to invite you to carry on this dream. So the work is not finished. I think we are on a very nice road. Let's continue with that. And with this, I would like to thank all the people from the One Group, certainly also all the people that contributed to the success of this winter school, and also my colleagues from IMO Mech. And I thank you for your attention.